Great. So let's start today class. We talk about game theory all over, but more recently we have talked about uh, just what's this one? Yeah. So more recently we talk about auctions, which is a very important part of computational game theory because there are both computational aspects and game theory aspects. Um, we talk about the basics of auctions. We talk about like the main uh, one of the main current motivations for auctions, among lots of others, is like essentially advertisement auction. I talked about it uh, in the 2 sessions ago. Now, and we talk about the basics of auctions, about essentially English auction, Dutch auction, first price auction, second price auction. And I mentioned these are the whole idea is that there is a first price versus second price. Also, I talk about the reserve price. I mentioned that reserve price is another thing that we will talk a little bit more about them. That's also another part of auctions which are very important. Uh, and these are also truthful auctions. It means that if you lie for a reserve price, you don't gain anything. What is the idea? Because this is a fixed price. Now, if your price is lower than that, if your valuation lower than this, so this is essentially you say that this is the reserve price. So this is I'm talking about. We talk about first price, second price. Another one which is very important is reserve, essentially called reserve price. We will talk more about it. But the idea is that, I mean, this is a reserve price that is there. These are truthful. What is the idea? The same idea that we have proved essentially for the second price action. When there is a reserve price, either you're essentially you need to do case analysis. If this is the bidder valuations, if it is less than that, then of course it is less than that. If you bid more than the amount that you have, it then you lose. If you put that amount or lower, you don't get it. So either way, it's better to don't lie. And the same thing here. If it is greater than reserve price, greater or equal to that, yeah. If you give the essentially, if you bid, if your bid is equal to bidder valuations, then or like your bid is like this, then it is higher. How much you are paying? Always you will pay reserve price. So independent of what is your bid that you are mentioning, you will be charged the reserve price. And so if you lie, you don't gain. So that's the idea that uh, this reserve price is another very important and very simple. Like we have first price, second price, and reserve price. These are like three very important uh, type of auctions that the people are using it, or the combinations. And we will talk more about them. So one thing that we want to talk more about it. So far we talk about offline auctions in the sense that, I mean, you will take all this essentially bids and then you will decide who is that. Here in this today we want to talk more about the online auctions. Online auctions this is in particular, for example, advertisement auctions are one of these because there is one essentially ad slot that is coming or impression that is coming, and you need to fill in with one of the creative that you have. And that's it. If you don't fill it, it is gone. And not only that, so each of these creative belongs to some of the advertisers. And these advertisers have some budget, daily budget, sometimes hourly budget, monthly budget. So when you assign this guy to this person, this ad slot to this, you will charge this guy something and then you are gone. So, but something from the budget of this person has been reduced. So in some sense, you cannot compensate it if you didn't essentially do a good pricing for him or her, or if the budget, you run out of the budget, then you run out of the budget. Potentially this ad slot that is coming, so this is the essentially ad slot for display ad. So there were several advertisers. So this is the advertisers 1 to say N. And then you could give any of them, you could give this one. But for example, if you potentially there is a next advertisement at the next time in the future, that you can give it essentially to this advertiser, essentially 1. But advertiser N, that person does not want it. Good. So here, if you, and say advertiser one has only one budget. So here, the first time, this is the first time, this is the second time, essentially. So when this display ad is essentially coming, you will give the the creative, it is called the ad for advertisement one. So you will give it to here. Then it has budget one, and you say charge it $1. So this guy is gone essentially. So then next time that this another ad is coming, you cannot assign it to this person because the budget is gone. However, if you have done more smartly, like when this advertisement slot is coming, you gave it to advertisement N. So you will assign this guy here, then you get say $1 here. And the next time that this second advertisement slot is coming, at that time you could give it to advertisements too. So essentially, if you are doing it smartly, you can get $2 say here, but if you are not doing it smartly, I mean, you may get only $1. And this is a typical actually example of these things that if you are not careful, this is also this idea of maximal matching versus maximum matching. And the idea is that if you are not careful, you may lose a factor 2 essentially. And the factor 2 is a lot in terms of money. You just think about that your salary goes half essentially, or the revenue of this particular company goes half. So half may be not bad for some things, but it is very bad for salary and for your income, etc. And this is a typical example that I have mentioned. And all of them are because of the online nature. Why? Because this is the ad slot that is coming, right, the first one. And then there is a second ad slot that is coming later. And the issue is that when this ad slot is coming, you don't know whether the second ad slot is coming or not. And that's the thing that makes the problem much harder. Now, we are seeing more of that, essentially, this kind of online actions for dynamic environments. This was one example that I have mentioned for ad slots connecting to the motivations for advertisement actions, which are actually online actions. But let's see what else, what are the other motivations. Consider this is another example, essentially. This is a last minute tickets. Say, this is this lady, she wants to run essentially an auction. Says, please bid your value and your patience. So you will come, you want to get essentially a ticket. This actually happens, like you want to get even this ticket can be some kind of basketball ticket, or football ticket, or something like this, or the movie theater ticket. And she said that please bid your value and your patience. A decision will be made by the end of your stated patience. Good. That whether I will give you this ticket to you or not. And you will see the example. So here there are three bidders essentially, 1, 2, and 3. The value, the bidder's value here is, when we say value, generally means bidder value. 180, 60. That's a value that I can pay for this. But of course, I try to get always profit. I want to get cheaper. I will arrive at 11 a.m., like the first person. Then the second one is 11 a.m., and the third one at 12. And their patience would be 2 hours. They can wait for 2 hours to essentially make this. After that, they are gone. Good. Then the question is, how should you bid, or these bidders, they should bid? Yeah.
So you should bid a 1 unit larger than the current loss value, and say your patience is 1 second. Therefore,
yeah. These are actually much deeper. So this is the one thing that this is actually a lot of research is going there. So you need to think a bit. I mean, it's good as a one initial solution, but you will see that there are lots of complications. Yeah.
So you arrive in order to buy tickets.
Yes, I mean, you will come to this lady and say, okay, I arrived. I want this $100. And then this lady said, how much you have essentially patience. So I will be here for 2 hours. I will be around 2 hours. Okay, you can go. By end of the 2 hours, I will decide whether you will get it and how much you need to pay. And of course, I don't want to pay more than this. I generally like to get truthful mechanisms. Truthful mechanisms are very easy because you will get the burden of bit shading out of the bidders or advertisers, like, or the people here, because bit shading is not that easy. You need to know a lot of things about the auctions and how much you want to decrease it, etc. And not it is for the people who don't have that computational issue, it might be actually quite involved. So you really want to get the this type of like you want to get a truthful actions or strategy proof action, or say incentive compatible. So these are three words: truthful, strategy proof, and incentive compatible. All of them means the same thing. You want to get those type of things because then there is no burden on the essentially bidders to lie about their values. Good. So now the setting is clear. Let's go how we should do that, or how it should be. So, but let's see a little bit of, the things here. So what will happen if everything is going well versus not? Good. Good. So if this is the first one. So if everything is going truthful, what will happen? Truthful means that nobody lies about this. So this is the auction that she is running. Say that I will sell. This is the rules of the auction. So she mentions now clearly. I will sell, the lady sells one ticket in each hour if there is a demand to the highest bidder at the second highest bid. So she wants to try to actually make it truthful. She tries that, okay, you don't need to lie, because anyhow, she's the lady, maybe the money does not come directly from the ticket price, the revenue. So, okay, I want to have a fair things, and she knows about, say, second price that is a truthful. There are, again, mentioned three important ones. Essentially, first price. Oh, so first price, second price, and reserve price. And these two are truthful. This one is not truthful. I like truthful the best, but as I mentioned, two other words it is used is strategy proof or incentive compatible. It all means the same thing, essentially. So she knows about it, say, I want to make essentially second price and make it essentially like truthful action. So you don't need to lie anything about it. But essentially the idea is that when you have it, the online things, that truth, this second price works actually in the offline setting. But and again, under this condition that there is no collusion, etc. But in the online setting, that simple second price does not work. So she said, okay, I will do this one at each hour. I will just do that. And then I will run a second price action at the end of each hour. She's thought that, okay, maybe that's a truthful action. That's a very good one. And she's very happy about it. Let's see whether it is correct or not. So if it is truthful, at the end of essentially like our 11 a.m., there are two bidders there, 180. So this is the bidder 1, 2, and 3. So one gets it at the second price, which is 8. Now, what about at time essentially the second one? It's like between at the end of, say, so this is 11 to, there are 2 hours essentially. We have two intervals, 11 to 12, and then we have 12 to 1. So at the end of like close to 1, essentially, there are, so the 1 already got it. But here, the 2 and 3, both of them are present. And then who gets it? 2 gets it because it's $80. How much does he or she pays? $60 second price. So that if it is somehow everything goes through. But what about if it is not the case? Good. Okay. So in this case, bidder one actually can, though it is a second price, seems that the bidder one actually can get a better price in two ways. One, the bidder one can reduce its bid price to only $65. Now, what will happen? At the end of our like 11, close to 12, then there are two people there. One is 65 here. The other one is 80. Who does get it? I mean, the 80 guy. The second person is get it at the price that he pays. It would be $65. So actually, he gets the second person, he or she gets the higher price. Because before it was just paid essentially $60. Now it is $65. Now, what will happen at the end of our two? Then there are two people there remaining. This 65 guy and the 60 guy. And then here, he or she get it because it's higher. And what is the price? The price would be second price, which is 60. So you will see that actually the whole revenue goes down. It was 140, now it is 125. And also the second person gets a cheaper thing. Sorry, the first person. But here the second person slightly pays more. Another way, they can, this is another interesting thing about the online, because everything, when we talk about online, means time matters. So here, this is another way actually that this person can get a benefit out of it. So let's see this one. So this is the case that this person actually it just it comes to the auction, but does not announce that I'm coming. So I don't don't show you. I mean, essentially just delays arrival to be at 12 p.m. instead of, because anyhow I'm here, I'm not waiting essentially. So then what will happen? At the first hour, they're essentially close to 12. This is only this person is present, the second guy. Only the second guy. So $80. So there is no second bid here. Second bid essentially would be zero. That's the thing you can consider the reserve price of zero in some sense. So that the second buyer actually gets it two and pays $0. What about at end of the R2? Then in that case, this guy is $100. This is present, and this is present. And then the first person gets it, the winner, and just pays $60. So in this case, somehow everyone gets the benefit except the auctioneers. And anyhow, she wanted to put something that if people lie, you cannot. But this is the idea. Actually, designing truthful mechanisms are very hard. Generally, it turns out lots of them are somehow a combination of second price plus reserve price. And then the reserve price, of course, you may change sometimes the reserve price at different time. That you can do it. But you need to be careful. But anyhow, it's not a very easy thing, essentially, to do that. And sometimes, actually, as we will see, it can be the case that the truthfulness can make the mechanism essentially less efficient, I will say efficient for the auctioneer. It means that the revenue can go down. We talked about it essentially before. But anyhow, designing a good one is not an easy thing. Even here, for example, the lady maybe didn't care about it, just want to make sure that these people, if they lie, they don't get benefits. But it is not the case even. So this problem, of course, this problem that I have mentioned is just some kind of, it's a good story. But maybe not that much in the real world is important. How even I will say that this is might be relevant. So, like for example, there is a basketball games here. So if you are not a student, if you're a faculty, then you need to pay for to go to the basketball games or football games here at UMD. And then they have some kind of auction. They don't, for example, they are somehow sending free tickets for you, but they don't send it at the beginning, because if you send it at the beginning or very early on, then the people don't have any incentive to buy. So okay, I will just wait if I get a free ticket or not. And when do they give the free tickets? They give the free tickets very close to the end, if they know that they have not sold enough. It somehow actually is better to keep part of the stadium like empty, because the people know that not always the price goes down. So you don't want to always, because if this is exactly this idea that we mentioned. So here, this is the arrival time. If I know that at some point, if there is a space in the stadium, they will make it free, then I don't buy essentially. So okay, I just don't buy, let them make it free, and or like much cheaper. I will get it at that time. It's better actually to keep part of the stadium, even though it is essentially empty. You don't want to give the free tickets, because if the people understand that you will give the free tickets, that then nobody buys. So you see, this is a very simple example that I'm saying here. And then you say, oh, all these auction things are coming. And this is very important, because you want to give actually exactly, this is the idea of the truthful mechanism. Because you want to say that people say, okay, I don't want to pay anything. If it is free, I will go there. But there are some other people that they are willing to pay essentially. But if you don't put the mechanism, like this guy, the 100 guy, the value of the ticket for him or her was 100 actually. He could potentially pay for that. But say, oh, I'm not stupid. If you can run something that I can get it for free, I think I was hearing this one, that the money does not essentially grows on trees. With the example. So nobody wants to lose their money. Yes, I know the value is 100, but if the value is 100 and I get it for free, then it will be much better. And so designing such kind of mechanism is hard. And these are essentially are everywhere in computer science. So these are just some examples. These are just dynamic problems. This is some older versions about essentially MotelLab or PlanetLab. These are all of this essentially some kind of, nowadays I will say lots of these actually are coming in the cloud computing. So grid computing, all of them nowadays essentially becomes a cloud computing issue. Cloud computing is very important. If you go, for example, to get something at Google G Cloud or at AWS, then you will see that you can actually pay differently for different hours that you are using. That there are lots of actually auction things. And still, I will say that actually the cloud one, it is still not too many people know about even the problem. There are lots of very nice things, that how much you can charge and what are the charging scheme. And still essentially very like uncharted waters. You can do much more research there. There are some, it was in the earlier version, distributed sensor networks or some other, or this kind of grid computing, but cloud computing adds more to that. So there's this kind of, for example, network resource allocation. So this is a dynamic negotiation for Wi-Fi wireless ports at the Starbucks. That can be the case. That like you can, and you don't need to do it that. There might be some apps that actually doing this one for you, but you just want to download that app and then use the app to get the cheapest price. The same thing you can do it, for example, for airplanes. You are playing it. Maybe I don't want to pay $10 essentially for 1 hour, but airplane anyhow it has some space. Maybe you can just do some kind of lottery, some kind of auction essentially to get cheaper. And again, everything can be done through the apps. And as I mentioned before, these systems are both computationally and economic systems. And of course, the more recent one, of course, are the eBay, for example, is one of these. Advertisement auctions are another example of this. So advertisement auctions, eBay, or this kind of things, for example, air ticket. All of them are like the modern world things that you will see the prices are changing, and all of them are based on the auctions. So. Good. So these are very important. And again, the main part is that these are some kind of temporal aspects. There are some time aspects in this one. The people are coming and leaving the bidders. Then it becomes much more complicated. This paper that I presented is one of the early papers in this area, especially about the online auctions, that is design some interesting results here. Good. So let's now talk about this online selection problem. Actually, this is one of the problems that I have used a lot in my life. I can buy some stuff, essentially, real estate or others, even actually for a stock. So this is something called secretary problem. There's another one called profit inequality that you can read. These are the two famous ones, actually, that I'm very glad that I was like one of the co-authors in these two papers. These are something that were known in the math community or statistics community before, but not for computer scientists. These are the papers that actually that were papers of mine that brought the attention here and then got lots of attentions here, essentially, in the CS, and essentially computational game theory. Okay, so let's see the problem. This is the online selection problem. And this is from that paper, essentially, back in 2003, 4, essentially. So say remove incentives. So we were talking about, so far we're talking about incentives, means being truthful, etc. We want to just understand some case that also this is another thing. So we were talking that these are these people are coming from this time to this time. So you can see that this bidder is coming here from here to here and wants it $2. This bidder is coming from here to here, it wants $5. This is the time, this is the patient time, and then when they arrive, and this is the valuations. Good. And we have this kind of time thing, that is the temporal aspect, which is time. So let's simplify the question is that, I mean, we don't want to talk about incentive for now. Just understand the case of we have disjoint arrival departure. That is even simpler. So we don't have such things like this. Everything would be something like this, that this guy and then this guy and then this guy and this. These are disjoint. What can we do even here? So let's see an example here. So this is 527 1003. These are the ones that these people are coming. Good. So these are the time that these people are coming. But let's see in the online things what will happen. So what is the problem? This problem called the online selection problem or the secretary problem. So here we want to remove incentives. Assume we have one item to sell. Just say one ticket I have even. And specialize this in the case of disjoint arrival departure. Like very simple thing. That's generally the thing that happens. The complicated problem is coming. You try to simplify such that you can get the essence of the problem. So this simplify is actually one of the leadership goals that Amazon, for example. It is very important. You will keep this big problem, you try to simplify such that you can attack. This problem actually, it reduces to the secretary problem. At that time, actually, was the Clinton was the Secretary of State, so that actually is a good thing. Secretary may have a little bit negative meaning nowadays, and the people are using. I learned to use it essentially, say assistant and stuff. You want to say you are secretary of this person, instead you will say assistant to that person. But anyhow, still we can say Secretary of State. So that's a very actually probably one of the best jobs that the people want to get in politics. Good. So what is this secretary problem that was originally introduced? You're interviewing in-job applicants. So they are interviewing in-job applicants. They are coming in a random order. That's a reasonable assumption because you don't know in which order they are coming, essentially. There is some randomness. You want to maximize the probability of selecting best applicant. say the total are n, and you know n. If you don't know n, again, this is another paper that we added, then the problem becomes hard. So among these n applicants, you want to essentially select the best one. Then you're given at any time, say there is an oracle that can ask the relative ordering with respect to applicants already interviewed. So what's the meaning of that? It means that, say, in this case, even you don't know the valuation. Actually, the valuation was part of this work that we are bringing, and so that there is a valuation, because in auctions, there is a valuation for the ticket. But in the original secretary problem, these guys, secretaries, are coming in random order. It means that any permutation has the same chances. If there are 3 people, there are 3 factorial means 6 things, and each of them is coming with probability 1/6. So one of them is coming. And then you don't know what is the valuation. The only thing that you can do, you can say relative order. I can compare any 2 secretaries, whether this person is better than this or not. I don't know any valuation. So it's a bit different from the one that we have it, but that somehow was closest to this setting that we had it. We consider the problem, the real world problem, try to simplify it as much possible, see what is the most related problem, that was secretary. Then we will see what can we do it, and actually we need to build on it. Good. So that's the thing. So these are 5 to 7. This, we know the values, and the question is whether the values can help or not. That was another paper actually that got the best paper award in some conference later. So whether the values really can help or not, but that's another thing. This was the first attempt to solve the problem. And in the original, again, you don't know the exact valuation, you only know the relative ordering. Okay. So let's see what will happen now. Good. So here, what is the idea? So the idea is that maybe first, I mean, the 5 guys is the 5 person is coming. The person who has a value 5. Then you might say maybe it's too early. And you know n. There are 5 people. Again, if you don't know the n, that's another story. But say you know. Then say, okay, I will maybe wait. It's just too early to accept something. Then you will go becomes 2. And then, oh, you become scared. Maybe the 5 was a good one. And the 2. Then you next time you will see 7. So, okay, that is good. Now you saw a little bit about the market and understood, okay, it was 5. I mean, you passed on, 2 passed on, but 7 seems good. Maybe 7 is the best value that I can get it. You will get 7. But then you don't know. The next time is the 1,000 guys. And the issue is that if 1,000 guy is not coming because of any reason, and you don't take the 7, then the next guy is 3. So it is, and you don't know the future. You know that you're coming from some random permutations, but that's essentially, you don't know this. So it is very critical for 7. At 7, you decide whether you want to take it or leave it. Because if you take it, then the 1,000 potentially can come. If you leave it, then 1,000 may not come and 3 comes, or even 0 comes. The problem becomes very interesting. And again, here I'm talking about the valuations, but you can always give, this valuation, you can think about the quality of this. So not only you can order essentially or compare these secretaries, but you can give a quality score to them. It is somehow, we have more information here, but still that setting applies. Good. This is essentially the secretary algorithm. I mean, it says due to Denkin, but I mean, you don't know at that time. They may attribute it to several people. So I knew that it was in Germany. I didn't. There was no World War Web that I can publish it or something. Even nowadays, the people are doing parallel work, but let alone there. So it's like you say, 1962, but maybe somebody got it essentially 1950. Published somewhere that the other people, like for example, in Russian, they published, and then I don't know, in English it is published 1962, but at least this is attributed to Jenkins. But there are, again, some controversy always for this type of things. Even, it's not that old. We are not talking about the, I mean, 2,000 years ago, talking about 60 years ago. But this is very important. That's the reason that the people, the attribute actually is important. So this is called essentially a stopping rule that picks the maximum element with probability approaching 1 over E. So this is essentially the following stopping rule that picks the maximum element with probability approaching 1 over E as n goes to infinity. What is the rule? Having said that, I will say this is one of the most practical algorithms that I have used it in my own life. Say, for example, as I mentioned, to buy, for example, a real estate or buy a stock essentially. So this is the rule that you should leave everything from this class. This algorithm you should know. What is that? You say that observe, and this is the constants are important, of course. Observe the first n over E elements. And E is a natural number, 2.7 something. Set a threshold equal to the maximum equality seen so far. Maximum quality seen so far. And again, it can be in the secretary, or because only say that who is the best secretary. You don't need to know the actual value. Say that who is the first guy in this, the best guy is this, the first n over E person. You will stop the next time that this threshold or reached or exceeded. So, and what do we know? We know that this asymptotic success probability of 1 over E is the best possible, even if the numerical values of elements are revealed. So essentially, this means that this is the optimum competitive ratio for large n's. For a small n, you may get a little bit better than that, because when n goes to infinity is the case. So here we were talking about a secretary problem. Of course, in our case, you know the valuation. It is not clear. You may say, okay, the valuation, where can it help? It can help you. Because, for example, if you know that all these valuations, so we were talking about these things. If you know that they are coming in a random order, but say in the previous example. So this is the example that we just talked about. If you know that the valuations are between 0 to 2000, then when 1000 guys coming, or like when 7 comes, oh, 7 is just too low. 1000, oh, that's actually reasonable things to take. So then you can actually do better selection if you know the valuation versus if you can just compare it. But the question is that, what about, you know that these are valuations, but you don't know the range, whether that can help you or not. It's not a trivial question. I mean, the people actually consider this is a trivial question, but the paper that formally proved this, he had some early proof as well, but this paper actually, I mean, came almost the same time. They got the best paper award in this economics and computation conference that I mentioned, just proving this fact that seems trivial, but it's not actually. So knowing the valuation can help, but the issue that knowing the valuation, but if you don't know anything about the range of these people, whether it helps or not, it's non-trivial. Because this kind of lower bounds in general, this is the coming back to this question of P not equal to NP. Why? Because sometimes you want to say that there is, I mean, if P is not equal to NP, you want to say there is no polynomial time algorithm. And then saying no polynomial is very, like, if you want to do just some kind of bound on the problem, this is some algorithm that you are giving. So this is the guarantee that it has. This is the algorithm that has this guarantee. But you want to say that no other algorithm, and this no other algorithm can be, I mean, any sophisticated algorithm. The algorithm may even essentially see what is the temperature, and based on that, maybe temperature, it can use it. Right? You can refute even those type of algorithm that can be. So that is the idea of this algorithmic lower bound, essentially, that you want to say something you cannot do better than that. This is actually the class that currently is I putting it on almost halfway essentially through the lecture. This is the graduate course that is on the YouTube. Again, there is a playlist for that. Please go and watch it if you are interested in. You will see the techniques there. These are hard things essentially. But anyhow, this is 1 over E is the best things. And why this algorithm? So there is a proof for that. I wanted to, I mean, this is the form, this is the whole proof essentially for this one. Why n over e is the best. I mean, you need to do some kind of probabilistic argument. I will skip essentially in the interest of time from this one. That's why you can, but that's the whole proof. You can just read it and essentially get it. But I want to say for now why this problem is, but the actual problem, this is actually very nice and simple proof. You can just read this one page and then you can check it. I will put it as an exercise. But so why this is practical? Say this is an important one where you can use it, or I have used it one of the instances. So this is the idea. Say you want to buy a house. Say okay, I want to go. I don't know I have the energy to go for 20 essentially house at most. This is n. N is equal to 20. So this is n is equal to 20 is the number of potential houses that you want to go. Maybe somebody say, oh, I want to go 100 houses. Okay, then you can go more. But that takes energy because you need to go to open houses. You may need to take the essentially agent to go there. It takes time essentially. So I want to, somebody say, oh, I don't want to go more than 10. I have actually seen some person, the first house that I saw, I bought it and I didn't think about it. But of course, you want to do some optimization. So n is the total number of things that potentially you want to do, not more than that. Then the question is that, but this is the online problem. A house is coming, especially in a competitive market. Like in a few days, it is gone. Even sometimes overpriced. Say it's not overpriced, but it is gone. So it's a hot market. It is called seller market. Then the question that you will go, if you want to wait for the 20, maybe the last guy that you will get it is much the worst one essentially. And you say, oh, I missed all those opportunities. I should have bought this house or that house. Like it. The question is that how many houses you should buy, how you have energy to go for 20. But the issue is that if you wait, because these houses are going, this is the online nature, coming and essentially gone in a few days. So you need to decide whether I want to buy this one. And of course, you want to buy the best among these 20 that you have energy to go there. Good. That's the synthesis algorithm actually becomes very handy. So you will say that, I mean, okay, I want to go. And the question is that how much you should wait. This is called something like exploration versus exploitation. How much you should wait essentially. To buy essentially these things. And this is one, I mean, you will compute it according to this rule. And this is the best thing that you can get. It is provably the best thing. And the proof is in the next page. Let's just show. You will just essentially compute 20 over E. I think, as I mentioned, E something 2.7 something. This is the E essentially. Just. And then you will compute this one, I don't know, becomes 6, 7 or something like this. It means that something else. Just get the ceiling because you want to get into it. They become 7. Maybe 8, okay. 7 or 8. Anyhow, you compute this one. Say, okay, it means that you should wait. You should go and see the first 7, 8 houses. You should not buy any. After that, the first house was comparable to the best that you have seen so far, that you should buy. And that's the best that you can do it. That helps a lot, actually. And again, I use it more than once. And it's several instances. That was just one example. So this is the one that you should know and try to use it. This is the thing that math helps you. Again, otherwise you might, some person might be picky and say, oh, I want to go 15. I'm very picky, I have some energy. But the issue is that if you go to 15, you lose money because you lost some opportunities that possibly they were good. Going more than that and don't buy is actually a loss for you. And going less than that and decide, that's also a loss. N over E is the actual. This is called secretary problem. It's very important. There's another one called profit inequality. That's, I mean, you can read more about it. that is also very interesting. That's also very simple algorithm. But let's go to our setting essentially that we discussed. There we can discuss this case essentially. So here, let's see our setting essentially. What is the basic setup? Say that this is a type. These are the things that the people are coming essentially to the auction. The type of a person, essentially the value that it has. It has arrival time, departure time, and the valuation we say WI. These are the discrete time periods. Arrival time is AI, departure time is DI, and valuation is WI. And there are K greater than or equal to 1 goods to sell. Now, I want to, based on this algorithm that I have mentioned, I want to make a truthful mechanism for this one. I want to really help that lady say, okay, I can help. And this is a paper, the first paper that we had. One of the early papers about online auctions. So, but the people is that you want to essentially be truthful. It means that misreporting arrival, departure, or valuation does not help the players. So assume that the K is equal to 1. Say for now we want to sell just 1. You can generalize it actually to more than 1. The other issue is that agents cannot underreport AI. Good. This is interesting. This is the part that actually, if you don't want to do that, if you just want to design by algorithms, such that if the person essentially can underreport their arrival time, then the efficiency of the algorithm would be too low. However, this is something that you can actually easily check it physically. That's always the same thing. That if you want to make it truthful, you can make it through algorithms, but the efficiency of the algorithm may suffer a lot. Sometimes it's better to do some physical check. And that is easy. Agents cannot underreport AI. Why? Because whenever they come, they should go and register. So they cannot say, oh, I was here from 8, like last night. Did you come and register or not? I said, yes, you can come here, and then you don't come to the system and register late. That is totally. And I want to prevent that as well. But you cannot just say, I was here from last night. That's not a reason. I can check it easily by some kind of, because sign up sheets. So these are some sort of mechanism design about truthfulness that you need to make it, if you want to design just algorithmically, would be too hard. In some sense, for example, this idea of Bitcoin was also coming, that how you can essentially do dollar virtually. And that was the whole idea of Bitcoin, essentially, that you have this one, means that there is some sense that, as I mentioned, the new technology may come. Some of them maybe later it comes, but we don't know. It's better to do just physical things. So yeah, the money is the cash thing, but now you have the electronic money or digital money. And an algorithm is called C competitive if we can get 1/C fraction of the optimum benchmark. So optimum benchmark, essentially, we will. So it is called C competitive for online algorithm. We don't say C approximation. We say C competitive. If you can get 1/C of the optimum. Okay, let me just mention the algorithm. So what is the algorithm here that you can just use it? So this is the first straw model we try. So we will set the price at the beginning. This is, as I mentioned, the combination. How do we design truthful mechanism? Through 2 rules, mainly, or lots of the time. Reserve price, it can be changed. The reserve price can change at different times. That's one of the truthful tools that we have. Other one is second price. So let's do that. Let's set the price, the original price. This is the reserve price. By price here, I mean the reserve price. So let's set the reserve price P equal to infinity at the beginning. Then so this is the price first is here. Then I will decrease the reserve price. Becomes the maximum the maximum valuation that I have seen it after seeing N/E, guys. This is the idea that I'm getting from secretary. So just at the beginning of the auction, if these people are coming, the price is infinity. Then at this point, this is N/E things. Then you will put a price which is the max of this guy. So this is the P here, then you will bring the P here. So you are changing the reserve price, but you need to be careful, because if you change the reserve price, actually can make the auction non-competitive or non-truthful. So at this time, so you will essentially bring this one P infinity, and then you are putting it P equal to max of these guys. So first these people, when the N over E people are coming, then you will put the max this, and then you will sell to the first bit, which is at least this P. After selling, then you put the price infinity because you have only one item. What is the issue? The issue is that, yes, this actually is a good algorithm if they don't have any intersection and these are just disjoint things. However, if this guy is here, is one guy that is coming here very early, but his patient or her patient is quite a bit. So the threshold is here. What is the idea? The idea is this one, that this person that comes here does not have any incentive to come soon because he knows that if he is coming soon, surely he does not get it or she does not get it. Why should I come essentially? Maybe you can put a higher price in the auction. Maybe in that case, you can hear this is something that is called malicious player. It's not benefit for you, but it makes the price higher. But why should I come essentially? So this person may delay and say, oh, I'm arriving. Just this person is there, by the way. This person is there. You see what is that? Say it's a clear essentially. It's not a sealed bit. You can see what are the bits that are there. So this person is there, but it does not formally come to the auction. Why should I come? I just wait. When the price is set, then I will come and get it instead of coming much earlier. So that does not work. You need to change slightly. And what is the change in this one? So you need to do a combination. So at threshold time tau, the threshold time is essentially when N over E guys are arriving. And note that this is a very general case. The people, this interval, they may intersect with each other. So at this arrival of N over E guys, you have two prices. Let P and Q be the two top guys that you have received. An agent bidding P have not yet departed exactly because of this issue. Then sell to that agent and breaking ties randomly. So if there are more than one person, just select one of them. And then how much you will give it? You will give the second price. So if this guy is present, if you are still present, there is a chance that you will get it. If at that time I decide, if you are not there, then you are not there. You cannot do it. But if you are there, I give it to the highest bid. What is the price? Second highest bid. So I'm using this second price. However, if there is no such guy, and note that I have only one item to sell. If it is sold, then it is gone. Then you will sell to the next agent whose bid is at least P. And here again, breaking ties randomly. So what I'm doing that, so first this P is infinity. I then bring it down essentially to this second highest price here. This is essentially the Q things. And then I will increase it a little bit because then I go, so if there is this person of highest price is not there, then I increase the price to this new price of the guy. And then that would be until I sell. And then again, I will make the price infinite. So instead of putting this reserve price, this, and this, I will put it this, then a little bit less, then a little bit more, and then actually you can show that this algorithm is, which is a combination of this things. You can essentially say that this algorithm, you can run it. This is the example that you can see it in the slides. And you can run it. This is still, needs a proof. And the idea of the proof essentially coming from these things. So this is the idea essentially. This is somehow the idea. Why this is truthful? If agent I wins, that the price charged to her does not depend on her reported valuation. That is super important. That was the whole idea of the second price is truthful, because the price that you will be charged, it will be independent of your value. So because it is a second price auction, essentially it is a truthful mechanism. So if you essentially you lie about your price, you don't gain anything. So and again, these two essentially comes as this first two things, are coming from the fact that if you if you understate your valuations or overstate because of these second price things that we discussed, because of the second price action is truthful, that doesn't help you. Okay, so pricing, price that one agent I is essentially facing is never influenced by DI. So what's the meaning of the departure time? Either you are in the market or you are not there, essentially. If you are not in the market, then you are not there. And if you are there, you can participate. So that really does not help you that much. But DI is essentially truthful. The only thing, as I mentioned, is the arrival time. Arrival time, if you actually, this is the case. If you can see that if you mention your reported arrival time is before your actual arrival time, that sometimes can help. But that we already prevented by some physical checks. And the whole idea is that if you essentially, you can, this is the whole, this is also the idea that, again, some exercise that you can do it. If you report, this is the idea that if there are two arrival times, AI and A prime I, it is always better to report AI if possible. So if essentially if you lie and you say that I came late, you can only lose, you don't get benefit. Because of the design that I have mentioned. Why? This is the idea that essentially if you are in the auction, this is essentially because of addition of this second price auction at the threshold time tau. But if you are still there, you will get it. So that's the proof that you can do it and you cannot do anything. Now, what about, one other thing, so far we only talk about the probabilities, the probability of getting the guy, 1 over E. But what about the expected, essentially, whether this is the efficient mechanism or not? What is the expected valuation that essentially you will get it? Like if you want to buy a house, what is the expected valuation? Of course, here you want to decrease the things. But here, this is the idea also for this one. This is the proof. So this is essentially the competitive ratio analysis. I want to see how good is my algorithm. So, and here we are talking efficiency. What is the meaning of efficiency? It means that I'm selling to whom? Consider the valuation of that coin. I want to sell, the lady want to sell to the person who really wants the best or the most price for this ticket. That's kind of efficient. It seems, like if a government wants to do that, I want to give to the person that who really wants this. He understands the valuation of this. So I will say the competitive ratio for efficiency is E plus order 1. So essentially this E, it comes, I will essentially be a factor E away from the optimum one, essentially. So why? There are two cases, very simple thing. So if this item sells at time tau, in this case, winners is highest bidder among the first N over E guys, correct? That's by definition. What is the probability that, so if these are random valuations, so this is 1 over E fraction of these people. What is the chance that the highest guys, it essentially comes here? 1 over E. That's the chance that can happen. So if we sell it at the threshold time tau, we get 1 over E, essentially expected valuation of this thing. But what about if I don't sell it here? If I sell here, then in that case, I use the secretary problem. I know that the auction picks the same outcome, like essentially the higher valuation with probability 1 over E according to the probability of the secretary problem. So either this case or this case, in both cases, I will get 1 over E. With probability 1 over E, I will get the highest valuations. And it means that your expected return would be 1 over E times the highest valuation. So essentially, we are losing 1 over E. That's essentially the competitive ratio. You can do more for this. You can make it essentially, also you can make something about the revenue of the auction. What about the lady? How much she sells, whether she gets a good price? Because the price, as I mentioned, this is efficiency, two things really important. to the people who really want it. And the second thing is that what about the revenue, the money that auctioneer collects? That's also very important. You can say that's also not bad. This is actually, you can get a essentially constant competitive for this revenue. And finally, this is the idea. So this was the idea that essentially we introduced this paper, this original paper. So if you have more than K items to sell, essentially, there are generally two phases essentially here. This is the learning phase, that here we are using a sequence of bits to set price for the rest of the auction. That generally it comes when there is some kind of thing to learn, essentially. You know, it's coming random valuations or something. This is the learning phase. Then there's some transition. You want to make sure from the transition that you want to apply, make sure that it remains truthful. This is the time that we were using this second price action at the threshold time. And later is the accept phase. Here we are essentially exploiting the information by generally putting the right price. So now we have information about this population. After seeing N over E, guys, I have a very good idea of what is this population, what are the values, and they are coming from some distributions. So I have it, then I will put a reserve price based on that, and then I will get it. This is, as I mentioned, this EC04 that actually gets a result for this and for lots of other problems. There are lots of generalization based on that. But this is the idea again, that anything that you want to design is this kind of online thing. This is some learning things. There is some transition part, that in the transition you want to make sure, because the people, even in the transition, the people can lie. If they know that for sure you are not giving to them, they don't, why there is any incentive for them to say that they even participate in the auction, because guaranteed essentially zero things for them. Then there's the accept phase, that now you have the information, now you can use it to essentially get the things that you do. This is the part that ML especially becomes very important. The learning and accepting phase, essentially mainly the accepting phase, that I mean, what is the threshold that you want to put it? This transition is the game theory part that you want to do. Of course, all of them is also the same game theory. Good. So I think I stop here. There are many more things about the auction that I mentioned. This conference, economics computation, that was one of the early ones that we had it. But now there are lots of papers. You can read a lot about them. But it was just some ideas to say that designing truthful mechanism, especially for online settings, that is a very common thing nowadays because of advertisement auctions or lots of other things, eBay, airline tickets, etc. That's very tricky problem and needs a lot of thinking and research and getting things. Okay.